So welcome back, everybody. And what I wanted to do today is to continue where we were last week, when we discussed some of the basic things with the transition probabilities, what we call the Metropolis-Hastings algorithm. And at the same time, we will take a kind of a top-down approach, where we are going to look at the equations which we need to code. Now, this is a kind of material which many of you may not have seen properly in a rigorous way. And I know that many of you may not have taken a course in mathematical methods like Fourier transforms, Laplace transforms, and so on. So is that something which rings a bell, a Fourier transform? So you've seen these things. Now, the type of formalism which we are going to use is something which is called the Fokker-Planck equation, which is a modification of the standard diffusion equation. So the kind of overarching entry point is that a Markov chain is actually something you can use to model the physical process of diffusion. You can derive the equation for diffusion from a Markov chain, and vice versa. So these two processes are intimately related with each other. So when we are using Markov chains now to move random walkers and pick points in space, we can adopt a lot of this machinery from the physics and the mathematics of diffusion. This means that we are going to look into a modified equation, which is called the Fokker-Planck equation. And that is going to allow us to have the random walkers jump in space according to a given probability distribution. And the probability distribution we have is the wave function squared. So let me quickly remind you of some of these technicalities. And I want to take this top-down approach first to show you what you need to code now. And then we're going back and try to link this Fokker-Planck equation, which is a modified diffusion equation, the standard diffusion equation, which you can derive directly from a Markov chain, is a diffusion equation with kinetic energy only. Now you can think of your objects moving in a field. So a modified equation is, let's say, a particle which moves with kinetic energy under the influence of, let's say, a gravitational field. So the force which you get then leads to a modified diffusion equation, which is called the Fokker-Planck equation. Now, in the slides here, you will find the derivations of this equation. And this is a long series of mathematical approximations which are made. And then together with the Fokker-Planck equation, there is something which is called the Langevin equation. So we will be a little bit sloppy with some of the derivations, but I wanted to give you the overarching view of where these equations come from and why we can use them. So the textbook by Becca and Sorella gives you an introduction to some of these topics, but I wanted now to remind you of what we need to code. So the Fokker-Planck equation is a modified diffusion equation because the diffusion equation, as you probably have seen it, contains only a drift term, a kinetic energy term, which is the first term here. And this F here could then be a force which is acting on the system. So think of this as like a particle moving in a gravitational field. Now, your system is described by a probability distribution. In our case, this is the quantum mechanical probability. And what you have then, when this P becomes time independent, then obviously there is a zero on the left-hand side here. And then you can actually solve this differential equation analytically. But we can also solve it with specific types of forces. We can actually solve this analytically. And we are coming back to that in the lecture today. Now, one of the things which is intimately linked with the diffusion equation is what's called the Langevin equation. So this is something you can think of as a displacement of a particle under some external force. So this is just the velocity, as you see, plus some random fluctuations. because you cannot nail down precisely where the particle is. There's always some noise together with the motion of an object. And this is something you can integrate up. So I'm just stating this result here. We will come back to that, the Langevin equation, a little bit more next week. But the way you're going to update your points is actually to take the previous position. This diffusion constant is nothing when you translate this into quantum mechanics as h bar divided by 2 times the mass of the particle. Because if you think of quantum mechanics, this d, the diffusion constant, which is a typical material specific constant, this is now given by the quantum mechanical h bar squared divided by 2 times the mass. And since we put h bar equal to 1 and the mass equal to 1, this becomes, for simplicity, just 1/2. So the kind of units we are using are so-called natural units. Okay? So the equation which we have here, after this manipulations here, which we went through last week, you can then show that this P here, this force, leads to an expression for this quantum force in order to have a balance when equilibrium has been reached, because when equilibrium has been reached, the left-hand side is equal to 0. Remember that what we discussed as one of the hallmarks of a random walk is that when you have reached the most likely state, or the stationary state, or the steady state as we call it, then the probability distribution is time independent. And then the left-hand side becomes 0, and then you can put a constraint on the equation here, which simply leads at this quantum force for the quantum mechanical object which we are using, because our P is the wave function squared, then this F has to be equal to this one. Now, towards the end of the lecture, we're going to list up again what we need to do technically. So we need a gradient. You will also need a gradient when you calculate the local energy. So we need the gradient of the trial wave function, and we also need its second derivative, which gives us the kinetic energy. Now, the thing which we are going to go through today is actually now a change in the metropolis test, because previously we've had a metropolis test where we only looked at the wave function squared in the new position divided by the wave function squared in the previous position. Now, this quantity which you see here is now representing this probability of making a transition. And this is a modified metropolis test, which normally is often called the Metropolis-Hastings algorithm. Because you, in the standard metropolis algorithm, we assume that going from x to y and y to x is equal. And that means that these two here cancel each other, with the factor out. So we only left with this term. And this is the standard metropolis test, which we have been implementing till now. This is a brute force test where we actually let the random walker, if we look at the equation here, jump with a constant multiplied with a random number between minus 0.5 to plus 0.5, because we wanted to jump between minus x and plus x, or minus y to plus y, etc. So the equation which we are going to derive from the Fokker-Planck equation, when you solve that, you can actually show that the solution is given by this quantity here. These are normalization constants for a Gaussian, but it's going to include this quantum force at a position x. Now, the other equation, when you go from x to y, so what this is saying is that you go from x to y, this is what this expresses, is the probability of making a transition from x to y in a time step delta t. So one of the assumptions we made earlier when we derived the metropolis algorithm was that this quantity g was time independent. But you can make it time dependent by introducing this delta t, which means that you're looking, this expresses the probability of making a jump from x to y in a time difference delta t. And this is given by something which is a Gaussian lookalike, and we will see why this is a Gaussian. And what we need to calculate then is actually this ratio here. And that means that we need to calculate the gradient of the probability distribution or the wave function. So technically, this means that if we now dive into the code example, this is a case for two electrons in 2 dimensions, where we last time what we discussed. So let me just bring that up here again so that we remind ourselves a little bit of what we discussed last time. So the system which you're going to see in examples, which you can copy fully, is a system where what we have is a trial wave function, psi of t, for 2 electrons. It has an electron position 1 and an electron position 2, and then it has 2 parameters, alpha and beta. These are the variational parameters. And last time, what we did was to think of this as 2 electrons. This is the system I'm using in the lecture notes. These are 2 electrons which move in a harmonic oscillator potential. So you have 2 electrons and they interact through the Coulomb interaction. So this could be electron 1 and this is electron 2, and they move in this harmonic oscillator potential. Now this trial wave function contains a harmonic oscillator part, which you can set up as before. So this is exactly what you have in project 1, plus R1, R2. And in this case, R1 or Ri squared is actually the same as xi squared plus yi squared. So we are dealing with 2 dimensions. If we had 3 dimensions, we would simply have c squared as well. So this is the position of one specific particle. This wave function here is then multiplied by a so-called correlation part, which ensures, as we discussed last week, that the divergence in the Coulomb interaction is cancelled by a divergence in the relative kinetic energies of 2 particles. And what we had then is a function which we can modify a little bit, which is going to be given by R12, which I'm going to set up pretty soon now, of 1 plus beta, and this is the new variational parameter of R12. And so this R12 is nothing but the difference between x1 minus x2 squared plus y1 minus y2 squared. Now in project 1, your correlated wave function is going to be slightly different. But what we need now is obviously from a computational point of view, we need this quantum force, which is going to be given by 1 over psi t. So this is a vector of del of psi t. And this will be a component for each particle. So we need that. That is one element which we need. And we will also need that one when we calculate the kinetic energy. Then what we need is the kinetic energy in the local energy. And that kinetic energy is obviously now given by the delta I squared of psi of t. And then I have to sum the total kinetic energy is then obviously the kinetic energy of the 2 particles. So you sum particle 1 and particle 2. So this is something which we need to implement. Now in project 1, till we have included everything, we are actually just going to use this first part of the trial wave function. So when we're looking at this system of bosons, in the beginning, we are going to develop all the machinery with just this simple one-body part. So what we did last time is that we call this a one-body wave function, OB, one body. And the second part, which is this one, is something we call the correlated part or the Jastrow part. So we often use a C for correlations. So the general trial wave function for a given system, psi of t for R, which is now a container for all the positions of the particles, is given by one function, which is the one body density, which may depend on some of these parameters, and multiplied with a correlated part, which also depends on these coordinates in some kind of way. So that's a typical trial wave function which we end up with. But in the beginning, when we are going to develop all the machinery, we are just going to use the one-body part of the wave function because the derivatives are simpler and we know the analytical answer for the results. It's just the harmonic oscillator energies. So if I do 10 particles or 100 particles, 1, 2, and 3 dimensions, we know exactly what we should get. Okay? And life is also simpler because we have only one parameter to vary. So that means that in general, the type of equations we end up having to implement are a little bit easier. But when we include the correlated part of the wave function, life starts to get more complicated. And then we need to be a little bit careful when we calculate this term and also when we calculate that term. And you can see that quickly because if you now look at these, let's say the second derivative of the trial wave function for a given particle. So let's take psi of t. This is nothing but delta I for one given particle of the one-body part, where we now have to single out the specific particle we are looking at, multiplied with the correlated part, which now depends on the interparticle distance and the variational parameters. So which means that when we look at this term here, and what we are going to calculate is something like psi of t of del I times psi of t, you will see that this will now contain, if we just use the standard chain rule for derivatives, there's going to be a term which is del I of phi of one body, second derivative. And now I'm skipping r and alpha as parameters in phi of b. And you see now that this will just contain 1 divided by phi OB, because if you take the second derivatives here, then the term psi of c, which you have here for that term, psi of c, is factored out by a term there. Then what we need is obviously plus. There's going to be a slightly nastier term, which is actually going to be given by del I of psi OB multiplied del I of psi c. So this is more complicated, plus a final term, which is going to be given by 1 over phi c, and then I have the second derivative with respect to the correlated part. So this is just an application of the chain rule. And similar equations are equations which we will get from the quantum force. So if you look at the quantum force piece, the quantum force will also include a term like this one, but not with delta I, but you will actually have a term which goes like delta I, and then I have to look at the product of these two guys here. So when we include the correlation part, life gets a little bit more complicated, okay? So this was just a reminder of what we did last week when we discussed the type of function which we have in the lecture notes. So let's go back to the lecture notes and just take a look at the way you need to implement it when you now want to include important sampling. So let's take a closer look. So the first part of the code here is just us setting up the files which we are writing data to. And this is a 2-electron code for 2-dimensional quantum dot system. And you see now that the trial wave function contains these parameters alpha and beta. You transfer the positions of particle 1 and particle 2. So this is now an array. Particle 1, x is 0, and this is particle 1 for y. So y is 1 in this array. So I'm just transferring R as a matrix. So the first element of the matrix is the particle, and the second is x, and this is y. So this is just R1 squared and R2 squared. Then I also set up the distance between the two particles, the relative distance. And then I calculate the denominator in this specific equation I have for the trial wave, for the correlated part of the wave function. This is nothing but the single particle piece, and then I add the denominator here. So just pay attention that I I don't calculate the exponential twice. This is to save CPU cycles. An exponential is time consuming. So I calculate all the arguments for the exponential, which now contains the correlated part plus the single particle piece here. Okay. Then what I've done is actually to go through the analytical derivation of the local energy. So for two particles, this is okay to do by paper and pencil. It's still error-prone. It's easy to make small errors. But you see, again, I have the position of particle 1, particle 2, and R12. This is the term which you have just from the harmonic oscillator part. And then the other terms which you see, this one comes from the correlated part of the waveform. So this is my local energy. Then I calculate this quantum force. So I calculate the quantum force for both particles. In this specific case, I'm moving both particles first, and then I do the metropolis test. But as I told you, it's more convenient to move one particle at a time. But in the examples I have, since I'm just dealing with two particles, I move both particles, and then I calculate the new trial wave function. So the example I have here is not optimized with respect to computational efficiency. So I try to make these examples in the lecture notes more straightforward so that you can follow the equations. And I have not put in many of these computational considerations. So from a computational point of view, it's more convenient to actually move one particle at a time. But here, as you can see, I'm calculating this quantum force for both particles here. So I set it up for particle 1 and particle 2 here. And this is now position XY and XY here. So that's that part. And then I'm doing 100,000 Monte Carlo cycles. So my old position is simply, I first zero them. I calculate the quantum force old. I'm just zeroing out quantities. So I'm just setting everything to 0. And now I run through these variational parameters. But in this case, I have alpha values and beta values. So I'm running over two parameters. And I'm just making an array over these parameters. So my old position is now given by this normal distribution times the square of this time step, which is a variable, which normally we would tweak a little bit between 10 to the minus 3 to 10 to the minus 1. So we often make a calculation between these values, and then we extrapolate that to 0. Then you see this is the old position, and then I calculate the old function and the old quantum force. This is the quantum force in the old position. Because at the end, if we scroll up a little bit, we are going to calculate this ratio here. And since this depends on the quantum force in X and the quantum force in Y, we need to calculate the quantum force in the new position and in the old position. So if we scroll down then, you will see now I'm starting the Monte Carlo cycling. I set up a new positions. I have a normal distribution with mean 0 and variance 1. And then I take this quantity and add the old quantum force times this step times this diffusion constant, which is just a half. Then I calculate the new quantum force. My Green's function, as you can see here, I don't calculate the exponential for the denominator and the numerator, but I calculate the arguments. So if you look at the equation which you have, if we just go up again, you see now that these factors here disappear because you're taking a ratio. But then you have an exponential. So you have an exponential in the denominator and in the numerator. So that means that you, instead of calculating two exponentials, I calculate the argument to the exponential, which is a ratio between the numerator and the denominator. Because calculating two exponentials is also time consuming. So I calculate these arguments, and that is what I call the Green's function here. And this is set up here. I run over the dimensions. And as you can see, I'm moving the particles. And what I do now, I get a new probability ratio. And I take the Green's function. I'm not putting everything into exponential. This is the new wave function squared divided by the old one. And this is the one which I use to compared with the Monte Carlo, no, the previous positions and a random number. So this is my Metropolis test, what you have here. And it's normally called Metropolis Hastings because we have this transition probability for which we now have a model. So this function, the Green's function, is the same as this object T, which we discussed in the lectures previously. And then I update energies. I have the energy expectation value, the variance expectation value, and then simply write out here. And then the calculation is done for 10 variational parameters for alpha and beta. I have 2 particles in 2 dimensions. And then I can make a, oops. Oh yeah, I have to actually this is something I have to change, right? Yeah, this is outdated. Sorry, I need to change that one. I can't display the figure here properly. So I'm going to fix that one in the break here. Sorry, I didn't pay attention to that. But basically what you need to do now is to change your Monte Carlo calculation and calculate this Green's function object and have a function where you're setting up this quantum force. So you can use these examples for the harmonic oscillator case for the bosons, because this is pretty straightforward to implement. Any questions? So this is a top-down view of what you need to have in your codes. And this replaces the brute force Monte Carlo sampling, where you simply let your random walkers jump according to a new step, which is given by a previous step plus a constant which you tune, multiplied with a random number. Now we are letting the random walker follow the probability distribution which we are dealing with. And this is given to us by this Fokker-Planck equation. So one of the things which I wanted to do is to give you a little bit more of the background of the mathematics of importance sampling and the Fokker-Planck equation and the Langevin equations. So I will go through some of the material here before we go back to the whiteboard. So the typical thing which you end up doing, and which we discussed previously, if we go back to this detailed balance condition, what we had is that we had an probability W, which is our Y function squared. This is the probability of making a transition. And this is now the probability of being in a state 0 here, right? And if you now look at a simple case where you have the Boltzmann distribution, so this W is the Boltzmann distribution. Suppose you now you just have 2 states only, 0 and 1. And there is an energy difference of delta E there. So that means that when this detailed balance has been established and you want to find the ratios here, you know that this quantity here is something you can calculate because you have the Boltzmann distribution, and the same here. And when you take the ratios of going from 1 to 0, 0 to 1, that is simply given by this energy difference exponentiated. And when you're dealing with a Fokker-Planck equation, one way to look at this, and we are going back to the whiteboard pretty soon, if we now look at an example where you assume that your initial distribution for being in a state I is just given by a Kronecker delta. If this is a continuous object, it could be a delta function. Now, if you do that, after some time step, delta t, you're in a new position, and then the probability is just given by your probability of being at t equals 0. Now, this is, if you look at the continuous case, this means that this W in a position X is now replaced by a delta function. So the way you could think of this is, suppose you take I mentioned this in the beginning, take a cup of coffee and you add milk to your coffee. So you could think of the milk molecules being distributed in just one point in space in the beginning at t equals 0. And then you could think of your milk molecules being represented by a delta distribution. That's an example. Then you know that when equilibrium sets in, these milk molecules spread out, they diffuse in your coffee, and then at a certain point you have coffee with milk, right? And your coffee changes colors, etc., etc. So this is something you can simulate with this process here, which is a Markov chain. which is just another way of writing down the diffusion process. So the way you would look at this when you do a continuous calculation with a continuous distribution is that you have your probability distribution, which depends on time. And then you make a step from x at the time t to y at the time t plus delta t. So this is an extension of what we did previously, where we assumed that w here was time independent. And that means that your new probability at the position y at the time t plus delta t is actually, instead of having a discrete sum, as you have here, you have an integral over all the positions these objects can be in. So this is nothing but the continuous variant of a Markov chain. And you have an initial probability, which is multiplied with the probability of making a transition. So if you do this after m steps, this simply becomes like that. And when you reach equilibrium, this t disappears. So this object is time independent. So you start at a time wx, and then you have this object where you move from x to y in a time t. Also note the change in notation here, because what I did was simply to say that I start with x to y, and normally then this object w is seen as time independent. Now, when you look at this object, there is something which we're coming back to in the lectures here, and that is about Fourier transform. So this quantity which you have here can be written as a Fourier transform of a distribution in momentum space. So this is the definition of the Fourier transform. And if you use the definition of the delta function, so if you assume that this is given by a delta function, then the delta function simply gives us then that this object here has to be 1 over 2 pi. And then you can use the Fourier transform, and we are going to look at this pretty soon now on the whiteboard. So the Fourier transformed equation, diffusion equation, is now simply an equation in momentum space where you make a transformation from x to momentum space. And this is an equation you can solve analytically, because this is just one equation which depends on t. And that means that your probability distribution is nothing but a Gaussian here. So that's the solution to the diffusion process. So that's a fundamental solution to the diffusion equation without a drift term. And the Fokker-Planck equation is actually a modification of this equation. So if you look at the Fourier transform you have here, you can then go back and find your distribution at the time t. You have a normalization condition. And if you do that, you will find that this transition probability of going from x to y in a time step delta t is given by this function here. Okay? So this is your probability distribution for making a transition from x to y at a time step delta t. Now, there is an interesting property here. If you look at the equation, if I now set up the ratio between this quantity when I go from x to y and when I go from y to x, and if you spool back a little bit, so let's just do that. If you spool back here and you calculate this ratio with just plain diffusion, what would you get then? So look at this ratio which you want to calculate, and then go back to the equation which you have here. This equation here, this one, and you take the ratio. So y, x to y, and then you divide it by going from y to x. And if you take the ratio of this one with the reverse process, what would you get then? If you look at the right-hand side here. So just interchange x and y in the equation. And you take the ratio. So it's not 0, obviously, but there's another famous number. Okay, let me give you a quick hint here. So let's go back. to the whiteboard. So when we look at the metropolis test now, what we want to do is actually a test, a new test, where we are calculating this function y of x, which is given now by the transition probability of going from x to y. And then this is divided by the probability of going from y to x. And then we have the wave function squared of being in the new position y, divided by psi of t of x squared. Now, when we did the standard metropolis test, we assumed that these two were equal. So that means that this simply gave us 1, okay? Now, what we have now, when we solve the diffusion equation, so with the solution of a diffusion equation where we now look at the probability P of d of t, and this has a diffusion constant, and then we have a second derivative of P, then this P is now what becomes the model for T. And in our case, this is going to be proportional with e to the minus, and then I have a y minus x squared divided by 4d times time t. Now, if I take the ratio of t of x to y and divide by t of y to x, what I have then is simply e to the minus y minus x squared of 4 dt divided of e to the minus x minus y squared of 4 dt. And this becomes equal to a famous number, right? So what's your choice here? It's not 0, obviously. That's 1, right? So this brings us back. So if I just take the standard diffusion equation, this means that the probability distribution I get is actually going to be a Gaussian. And if I take the ratios between the two probabilities, that is simply going to give me 1. Because you see now, this is a squared quantity. So y minus x, whether I write y minus x or x minus y gives us the same number. So it means that these transition probabilities are the same for the reverse process. And then I don't gain anything. And this is why I add this drift term, because that's going to change my probability distribution for making a transition. And that's where the Fokker-Planck equation comes into play. Because if I just use the plain diffusion equation, I'm actually back to where I were before. My transition probability, the ratio of that one, in the metropolis test, which you see here, gives me just 1. And then I'm simply taking the wave function squared divided by the wave function squared in the previous position. And that's why we introduce this Fokker-Planck equation as a way to mimic a process where the random walker now jumps according to the given distribution which we have. So in the notes below here, we have a derivation of the Fokker-Planck, but what I wanted to do now is just to go back a little bit and look at some of the basics and how we can actually interpret what we are doing as a probability distribution. So I wanted to remind you a little bit about these types of Fourier transformations and how they link with the probability interpretation, which I just put up on the whiteboard here. So let's now go back to the whiteboard and go a little bit back and forth and remind ourselves about Fourier transforms and the diffusion equation and how these things actually pop up. So if we now just simplify things, so I'm going to change my notation a little bit. So if I am in one dimension, then I'm going to let this just be given by a function which I call x of t. So this is a probability distribution. Now my diffusion equation without any external force is now given in one dimension by this function here. The second derivative with respect to the spatial degrees of freedom and the first derivative with respect to time. Then I can define some initial conditions. So what I'm doing now is just to go through some of the things which I put at a more overarching level in the notes. So you can define some initial conditions where we simply could say that this phi of x of t at time equal to 0 is given by some function f of x. So these are the initial conditions. And then we can put in the boundary conditions, because this is a partial differential equation. So we need both initial conditions and boundary conditions. So the boundary conditions, which we often implement, and in particular, if you do quantum mechanics, what we would like to have then, if this phi is now going to be given by the wave function squared, then we would like this in the limit where x goes to infinity, to plus or minus infinity, we want this to be 0. So that's a bounded problem. And in quantum mechanics, we need this boundary condition, because else the energy will not be a constant. It will diverge. It can diverge. So this is something which you then would apply for all t. So if we now look at the Fourier transform to momentum space, so let me remind you of some of these elements which I just threw at you quickly in the Jupyter notebook. So if you look at the Fourier transform in momentum space to k, so this is my momentum space degree of freedom, what I'm having then is a function phi of x of t, which then goes over to a phi tilde of k and t. And we know that this phi tilde of k of t is then given by an integral where I integrate over all x in the domains from typically minus infinity to plus infinity. And I have an e of I kx, and then I multiply this with x of t here. So that's the definition. And the inverse one has e to the minus k of x. So, and you've probably seen some of this, but I just wanted to remind you of that. So if I then make the Fourier transform of the differential equation, that means that I now get a differential equation of phi tilde of k of t of dt, which is actually equal to minus d, because now I take the second derivative. So we take the second derivative of this equation, and that simply gives us, and this is probably something you've seen before, and this gives us phi tilde of k of t. And this is an equation which we can solve. So it will have initial conditions, which is a phi tilde of k at time equals 0, which is then the Fourier transform of the function f. So when I put this tilde, this is the Fourier transform of, so that would be the same as the integral over d of x, of e of chi of x, and then f of x. So that's just the Fourier transform. And if I do that, before we take a break, what we find then is a unique solution to this problem, because this is just a first order differential equation. This does not depend on t. So the only thing I need then is actually to integrate up with respect to time. So this has a unique solution. When I then plug in the time and perform the integration over time from time 0 up to time t, this is going to obviously have the initial condition of k, and this is going to be of e minus d of k squared of t. So that's my unique solution. So this is actually this quantity which I have then, this phi of x of t, is obviously given by the inverse Fourier transform. Is given by the inverse Fourier transform. Which means that I would then have a phi of x of t, which is then given by an integral over k in the domain of k values, which is typically minus infinity to plus infinity, of dk of e of minus So I had plus there, minus I kx, and then I have to perform the Fourier integral of phi tilde of k of t. So if I now, after the break, we are going to assume then, as an example, so we take a small break now. So the example is Gaussian. So that means that I assume now that my initial distribution is just given by a Gaussian of alpha times x squared. Okay. So I'm just going to set up the integrals so that you can see that you actually end up with a Gaussian in momentum space as well. And this is going to be the general solution of the diffusion equation. Okay? Let me know if there are any questions before we take a small break. I went a little bit over time. I just wanted to set up the example which we are going to look at after the break here. And this is something which can be done, and probably you have seen these examples. By the way, one thing which I will be a little bit, how to say, not exactly sloppy, but some of the integrals, if we just do them on paper and pencil, can quickly take 1-2 pages. So I will just set up the integral and give you the answer. Because if we are going to go through all these integrations, then we're just going to waste a whole lecture on that. So I hope you can forgive me if I just set up the answer of an integral. Many of these integrals are integrals you can look up in tables over integrals, actually. So if you know how to integrate, there is no point in us here spending time on going through an integration. I hope you can forgive me for that. Okay? So let's take stretch legs a little bit and so what we are going to do now is simply to look at some examples. And I want to use these examples to link with the final equation which we are going to plug in, and why we normally interpret this as a transition probability. And this transition probability in the literature is actually called the Green's function. And some of you may have encountered Green's functions in a course in mathematical physics. But let's look at this example which we started with before the break. And we are now going to assume that this f of x, which we had, so f of x is our initial condition requirement on the probability distribution. So what it means is that at a time t equals 0, your probability distribution is a Gaussian. And that could be a model for this example, which I always keep repeating. I almost give you the impression that I know only one example, but that's because I drink so much coffee that it's thinking of a drop of milk in a coffee cup is actually one of the first things which strikes me. I mean, there's no blood in my veins any longer. It's only coffee which runs through my veins. But if we now think of that as a Gaussian distribution, we can then calculate these things. So let's look at what we get. So a Fourier transform of a given object is normally written as with an uppercase F. So that means us performing the Fourier transform we discussed before the break. So the Fourier transform of e to the minus alpha of x squared is given by also a Gaussian, but now a Gaussian in momentum space. And this has so this is an alpha here. It's a normalization constant. So as I said, I'm not going to go through the calculation of these integrals. I'm just going to state the results. I hope that's okay, because I mean, going through these integrations is not what we are aiming at. And this parameter alpha squared is actually something which we then can set up in terms of the diffusion constant times time. So t is in this case a fixed parameter because we are only looking at the integration with respect to x. We are performing a Fourier transform, fixed time. So think of time as just as a fixed parameter. Now, what we also have is that the inverse Fourier transform, and this is written like that, So that is simply integrating over the other variable and multiplying with e to the minus I kx or e to the I kx. And the inverse Fourier transform of this quantity of d of k squared, because now I'm just putting these constants which we have in here. Then what I have is just this expression. So the inverse Fourier transform is nothing but minus x squared. So I'm just setting in here the normalization constant as well. So this is a 4 pi of d times t. So what this is saying is simply that the time is, the function depends on a factor which goes like the inverse square root of time. So if you're thinking of a free particle, that would clearly move in terms of a function of time. But now we actually have, with diffusion, we have a factor of inverse time squared. So let's move on a little bit and look at the inverse Fourier transform. So we have, if we do this in n dimensions, it's pretty easy to actually move to n dimensions, and we will often just stay in 2 or 3 dimensions. In that case, the Fourier transform of this quantity of v of minus d, and now we actually have the absolute value here, k squared of t, that is the same as 1 over, and now I have a normalization constant which reflects the fact that I am in n dimensions, and this is given by the exponential of minus, and then I have x squared divided by 4 dt. So this actually has a name, this distribution here. This is also known as the fundamental distribution for the diffusion equation. Of the diffusion equation. So if I solve the diffusion equation, this is actually the kind of solution which we get, and that's why it's called the fundamental distribution of the diffusion equation. Now, a Gaussian distribution is also something which we are pretty accustomed with, and we also know that the Gaussian distribution is a quantity which we typically can think of as a way to model the probability distributions. Now, in our case, in project number 1, the harmonic oscillator wave function actually looks like a Gaussian distribution, because it goes like e to the minus alpha squared times x squared, and if you go to more dimension, it's x squared, y squared, and z squared, etc. So let's now just rewrite this in a simpler form. So if we take f inverse, I'm just going to replace that with a function. So this Fourier transform is something which I'm going to call for an object Sn, n for the dimension which we are in, of x of t. So this is just a function. And in our case, this function is that specific Gaussian. Now, there's another theorem which we are interested in, and that is the convolution theorem. So I'm assuming that you have seen the mathematical process of convolution. So the mathematical process of convolution says that a function y of t is given by some function x, and then we normally write the convolution sign with this asterisk, times some function w as a function of t, and that is given by an integral over a variable s. And this s is defined in a specific domain, which we just leave unspecified here. And this has an x of s, and then there may be a weight function where we have t minus s. So that's the mathematical definition of convolution. Now, this is often used in imaging. And for those of you who are following the course on machine learning, you've probably seen something like this. So you could think of X being the position of a specific object, and you're measuring X over time. So S plays a role of time here, if you want to. And you could now think of that for some specific times S, this X is not well measured. There may be a lot of noise. So what we would do then is to apply a specific filter which filters out some specific observation so that it takes into account noise in a way which we mean is physical representative for that specific noise, but it's a way to filter out some specific result. But mathematically, what you see here, this is the mathematical definition of convolution. Now we can actually use that object phi, which we have, our distribution, and express that in terms of this function S. So we can actually write this out as a function where we have a function f, and we take the convolution between this Sn, and let's just leave out the that one. And then we have a dependence on x and t. And this is something which we now can write out in terms of this probability distribution which we found, which is the fundamental solution to the diffusion equation of n12. We have an integral over all real numbers. So I'm just writing it like this, of this d and y. And then we have a function, which is our distribution y, which we are transforming here. And y is then multiplied by the exponential. And now we are taking the difference minus x minus y squared divided by 4dt, like that. Now, this equation, the way it looks like, this is something which we now can interpret in a specific way. So you could now think of u having an initial function f, which is your initial distribution. So think back to your initial condition. And then by using the solution to the diffusion equation, we are treating this as a transition probability from y to x. So what we are doing now is we are convoluting the original function with all the transition probabilities, and we are integrating over all these probabilities. So what you see here, in a way, is actually something which mimics what we started with, where we had a probability wi of t, which in the Markov chain was then given by this wj going to I, multiplied with wj over t prime. So this, what you see here, this process, what you have, is in a way, through the convolutional theorem, is a way to express the transition probability from a state f of y to a state which we have here at x at a time t here, but where we now have defined a transition probability. So this is the way we can define that in using the convolutional theorem. So now we can make an example here. We can now suppose that this original, this is the time independent part. So you could think of u starting at a time t equals 0. You have the initial conditions. This is your initial distribution, which you then want to see how it evolves. So if you look at this function here, we could now simply assume that this is just given by some constant, alpha divided by pi. This is just properly normalized. There is a phi 0 minus alpha times x squared. And this is normalized. So again, it's a Gaussian. It's normalized so that what we have now is that because this f all these quantities play the roles of probabilities. So we integrate R over D of X, of F of X, and this is normalized so it's equal to phi 0. So this is just a function I cooked up here. So that means that I can calculate this quantity phi of X. So this is a probability on being in a position X at a time t. And if I use that as an example, then I have a constant here. I'm going to have a new constant, a divided by 4 pi squared dt. And this goes like n to the power of, to the power of n half. And this is multiplied with, and then I have an integral over all the spatial degrees of freedom, dy. And this is then multiplied with exponential. And now I have minus this parameter alpha of y squared minus, and then I have x minus y squared divided by 4 dt. So this is actually a Markov chain continuous distribution. So we can write this down. This is a Markov chain continuous. This is a continuous variant Markov chain continuous distribution. And I can actually set this up in a specific, in a more compact way. So what I could do is actually to write this in a more compact way as follows. So I have an integral over the spatial degrees of freedom over d and y. And now I have my function phi of y. So that could be my initial condition. Notice that this is assumed to be time independent here. And then it's multiplied with an object, which I just simply label as this w, which depends on x, y, and t. So if you look back at what we had, then the quantity which you see here, this one, can be interpreted as a probability distribution, where you actually make a transition. So it's a probability distribution representing a transition. It is a Gaussian. And in this specific case, what we end up with then is a way to express things where we have an initial probability, we have a transition probability, we integrate over all the possible positions y, and then we end up with a probability at a new time. So if you think back of what you have here, then this is nothing but the Markov chain, the discrete Markov chain representation. And if we are assuming that we have the process of diffusion, then this quantity here can be given by a Gaussian. So if we do that, if we just bake in a Gaussian, if we perform this integral, so this is an integral which we can actually solve analytically, this one here. So I'm just giving you the answer because I mean, else we would just spend at least some 15, 20 minutes of setting up the integral. So I'm just going to set the answer for this equation here. And that is, so this probability distribution, when we plug in the various elements, so we have alpha divided by pi, and then there is a 1 plus 4 times alpha of d of t of n divided by 2, multiplied with the exponential of minus alpha, and then I have x, so I'm integrating away over y, and then I get 1 plus 4 alpha of d of t. So what you see now is that this is now changing as a function of time. If you look back at the probability distribution you had, this one, you had a factor of 4 dt, but now due to the additional probability you had at here, you are getting now a change in time which goes like 4 alpha dt plus 1. So that means that if you now look at this one, it's a probability which is going to change as a factor of t of minus 1/2 as a function of time. So that means that if you now think of this original probability at the time t equals 0, it could look like this. So this is your original phi of x. And then as time evolves, this just spreads out more and more. So, and it shrinks a little bit, so it becomes more like this. And this would be something which takes place at time larger than 0. And this would again be phi of x here. And this sounds natural, right? Because suppose now that going back to this famous cup of coffee of mine, suppose this is the initial distribution of milk in your cup of coffee. This is your border of the cup of coffee. Then after some time, and these are the borders, after some time you reach an equilibrium situation where the distribution of milk molecules may look like that. So you can see now that this kind of physical process, which we have exemplified through these distributions here, that makes sense when it comes to processes like this one. Okay, so one of the things which we are going simply more to discuss very, how to say, in a more loose form here, because the solution to the diffusion equation is also given by this function. So what is common to do now is to take this function Sn, which is a function of x and t, and replace that one with what's called the Green's function. So this is often written as a function of x and t and y at the time t prime. And this is also a solution to the diffusion equation. So we can actually find the solution to this equation here. So what it means is that we make a transition from a time t at a position x to a position y at a time t prime. So this is also the solution of the Green's function. If I now set in a d times del, and then I have g of x. So I'm just stating these things here without deriving them, because I want to link this with the Metropolis-Hastings algorithm at the end. So in case I'm solving this differential equation, you can show that this Green's function is a solution to the problem. And this specific problem can be solved analytically. So there is a time dependence, there's a spatial dependence, and I can solve this function analytically, and I can show that if I define t minus t prime, it's going to be symmetric in time. This function g as a solution to that differential equation, as a function of a time step delta t, is actually given by, again, a Gaussian, d of times a delta t multiplied with e, and this has minus x minus y squared divided by 4d of delta t. So again, this we said that the Gaussian is a fundamental distribution for the solution of diffusion equation. But that means also that this function g here, which is now, so this g of x of y of delta t, plays the same role as a probability distribution, a transition probability, plays same role as this probability of making a transition, which we discussed earlier. So for the physical process of diffusion, we can then find something which is called the Green's function, which is the analytical solution to this problem here, which then represents the probability of making a transition from x to y in a time step delta t. So that means that I can express my function. So if I now look at my function phi of x of t, I can express that as an integral over time as well. So from time from up to t, sorry, over dt prime, and then I can integrate over all of the spatial coordinates of dy n, and then this is multiplied with this Green's function, which plays the role of a probability distribution, a transition probability, y of t prime, multiplied with our original distribution, f of y at a time t prime. So previously, what I did was actually to assume that I started with a t prime, a function here, which where we had plugged in the initial conditions and there was no time dependence here, but we can make this more general. So this is a general equation. So we have a probability of being in a position y at the time t prime. This is multiplied with the probability of making a transition. And that brings us over all the times which we have and all the positions which we have to a final probability. And if equilibrium has been reached, then this one becomes time independent. So this is just a little bit back and forth with these distributions, which are being used in order to understand how we can figure out how to improve our metropolis sampling. So if we go back to the metropolis sampling, what we end up with then is a modified metropolis sampling, which is normally called the metropolis Hastings. And that means that the acceptance of making a jump from a position j to a position I is the same as the minimum of 1. And then we take the ratio. So j is position x, position y. We make a jump from y, and I is position x in the equations here. So I'm jumping into a state x, and I started in a state y. But now I'm having this Green's function. So where I now have the process of going from x to y in a time step delta t divided by g of y of x of delta t. Now, if I use this as an equation, and I use only the solution to the diffusion problem with a fundamental probability transition, which is this one here. If I only use that one, then this ratio is going to be equal to 1. And that's where the Fokker-Planck equation comes into play. So here now, this ratio is equal to 1 if g x y t delta t is just the solution to the diffusion equation. So that means the diffusion equation solution. So what I need then, I need something different. And the first thing which comes into play then is this Fokker-Planck equation. And that's where the Fokker-Planck equation comes in, which is also an equation which can be solved analytically. So the Fokker-Planck equation, and let's just set it up here. This can be solved analytically. So what we would have then is an equation where we have the probability distribution as a function of t, which is then given by the diffusion constant, and then I have d, dx. So let's just put it back in one dimension here. So let's just do one dimension. So this is d, and then I have a d dx minus this force, which now expresses an external field which acts on the system. times x of t. And this function can then lead to, or this specific function then leads to a analytical form for x, y in a time step delta t, which takes the following form. So let's just put that on the next page. It has a 1 over 4 pi of d of this delta t to the power of, so if we're now doing this in 3 dim, then this is given by 3/2. And then I have an exponential where I have minus, and then I have y minus x minus, and then I have this constant d, and then I have my f of x. This is squared divided by 4 of d of delta t. And now what we see is that we take the ratio between y, x, and delta t divided by g of x or y of delta t. This is then different from 1. And in our case, this f of x in the project, this is a vector, and it's going to be given by 1 divided by the trial function times the gradient of the trial function. So computationally now we need to calculate this quantum force. And you will find the examples of that in the lecture notes for this specific week. So you can look up these equations and see how that is included in the code. And we also need, this second derivative is also needed. No, sorry, this first derivative is also needed when you evaluate, when evaluating the second derivative with respect to psi of t. So these are computational elements which we need to think of. And next week, we are going to look at how we can program this efficiently. I will also repeat some of these things next week, and I will try to also bring in this Langevin equation, because the Langevin equation is the one we use in order to let the random walker jump in space. So let me just bring that back again here so that you have all the small gritty nitty details. So if you go back a little bit, so next week, we are going to try to wrap up this discussion of the Fokker-Planck equation. And we are going to look at how we can link the Fokker-Planck equation with the Langevin equation. So what becomes an important piece for us is, one, the evaluation of the quantum force, but also the way we are going to let random walkers jump in space. So this is the Langevin equation. And this delta t appears here because we are solving this first order differential equation as we would solve a differential equation with Euler's method. So the delta t is your time step if you think of a first order differential equation solved with Euler's method. So the delta t becomes a parameter for us. And that parameter is something which we have to include in the simulations. And typically the values which we would have then would be something like a delta t from 10 to the minus 3 to 10 to the minus 1 or 10 to the minus 2. Many people would calculate the energy in a range of these values and then extrapolate to delta t equals 0, because in principle, delta t should go to 0. So if you make delta t too small, then you barely jump. If you make it too large, you will jump away from where the distribution is non-zero. So tuning this delta t becomes like a tuning parameter, but now the way you jump is guided by the probability distribution which we have at hand, which is the wave. In our case, this f of x is actually just the derivative or the gradient of the wave function. So I will try to summarize many of these things next week. This is a function we need to implement. I know that not everybody has taken a course in statistical mechanics. In statistical mechanics, you will often see It depends on the type of course and level. You will find discussions of diffusion equations and Markov chains and also the Fokker-Planck equation and the Langevin equation. Now I'm just bringing in the elements and I'm trying to connect them, but I don't know if I've been successful or not. But the important thing for us is that if we take away all these discussions about Fourier transforms, the Green's functions, and so on, the way we can view this is that we simply need a way to guide the sampling, and the Fokker-Planck equation is one way to implement this.